Ready.
Should be live. Can you double check, Sahil?
Yeah, I'll check. Yep, we're live.
Hello, everyone. Welcome to today's episode of Quadcast. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome, everybody, to a brand new exciting episode of Courtcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode. So without further ado, let's get to it. So I guess Tim and Mikey, when I first was learning about physics, I didn't really come across like the notion of symmetry. In fact, didn't come up until much later. And typically, I would learn about equations of motion and initial conditions of like, if I throw a ball in the air and it like start in this position and throw it at some velocity, where will it be at some moment in time? To take like a common example from Newtonian physics. So I kind of want to jump to like essentially how like what is the significance of symmetry? Like in other words, like why are we doing this episode? I guess Mikey, I'll put you on the spot first.
Yeah, okay. So I think um maybe to relate it to like the example you just gave, right? Like so when you throw the ball, as we learned in like high school physics, you learn how the ball starts here and you throw with a particular initial velocity, you can predict the parabolic arc that the ball will take. But the reason why the ball follows such a nice mathematically clean trajectory that you can calculate easily, um, actually comes from symmetries.
Hmm.
In fact, I would go so far as to say that symmetries are the single one and only thing about the universe that makes it possible for us to understand the universe. So I guess maybe just to clarify that statement with an example, you can think of like planetary motion, right? We know that the force of gravity, um, it acts in an attractive way towards everything, and it depends on your distance. Um, so there's a kind of spherical symmetry in the way the gravitational force works, in that anything on the sphere feels the same effect being pulled towards the center. Um, could you imagine how complicated it would be if that was not true? If like the force of gravity depended on exactly where you are on the sphere and where you've been on the sphere, like that would be crazy. Like we would never have been able to figure out how gravity works if it didn't have some kind of simple symmetric pattern to it, like the spherical symmetry that we see it. Uh,
I guess one question I want to ask about that for before you jump in, Tim, is with this example of spherical symmetry, I do remember learning the one over R squared law back in like, high school physics.
yeah.
And there's a spherical symmetry associated with that because it doesn't matter what angle you're at, but more of like radially how far you are away. Is there any deeper reason of like why is that so? Like what I mean, just is it verified experimentally and we use that, or is there like a deeper theoretical reason that can be simply explained of like why there's this spherical symmetry?
I I would say it depends on like what do you mean by asking the question. Like what do you mean by
Mm.
science? So so if you just study equations, um, and like one of my advisors back in the day says, you're basically a technician. You're a calculator. You kind of know better than that. A real physicist tries to understand where those equations come from. So
Mm.
symmetries are actually the language of actual physics. Symmetry drives understanding. So, of course, at the end of the day, you can say, hey, gravity is the same in different directions. Experimentally, we see that it's spherically symmetric. You can argue that that's just a brute fact, right? And you can let's say explain it, be like, hey, look, the equations are just the way they are. It looks spherically symmetric. These are fine explanations, but there's something deeply unsatisfying about it. Like what if you can say, hey, what if I wrote down slightly different equations? The reason we prefer one equation over another philosophically is because of symmetry. I cannot imagine any other argument for it or against it. It's just that a spherically symmetric world is more beautiful, and it's also one of the cosmological doctrine, right? You look up, down, left, right into space, it looks all the same. So there is no reason for us to believe that nature wouldn't take advantage of this symmetry. So we postulate it as an axiom. So that's why, there are multiple viewpoints of this. You can explain this brute fact by experiments. You can explain it by a mere fact of an equation. Or if you're a real physicist, you would explain it using asymmetry.
Very, very interesting. So what you're saying is that like we should think of physics as kind of interwoven with symmetries, and mainly people today like um, think of physics from the viewpoint of symmetries. Is that essentially what you're trying to say?
Yeah, to some extent, and also the equations get very messy very quickly. It's very complicated. I know there's a common conception that physics is very complicated, but the goal of physics is not to make things even more complicated. It's to simplify things. And with that philosophy in mind, I think the concept of symmetry satisfies that.
I mean, I would go beyond that. I would say, so, you can imagine a universe that has no rules that are consistent with one another from one time to another. And in this universe, dragons just appear out of nowhere and disappear, and then you can't predict anything, right? Compared to our universe, where the sun rises at a predictable time every single morning, and this all relates to how the planets go around the sun. I would say that symmetry is like the difference between these two universes is that one universe exhibits patterns, predictable patterns, and the other universe doesn't. And I would say that symmetry is the most powerful language, at least we've come up with yet, to describe how patterns work. So if you're not dealing with symmetries, you're not dealing with patterns, you're not dealing with prediction, you're not doing physics.
I see. I see. So I kind of want to take a step back and get at a very basic level. So could we explain to the audience, like we've been using the word symmetry, it has an intuitive notion of what it means. Like, if I look at a triangle and I turn it this way or like rotate it by like I think 1/3 degree, I forget the exact amount of, but if you rotate a certain amount, it doesn't really change, like equilateral triangle, for instance. My question to you is like, from that aspect, is there a different way that physicists think about symmetry, or is it exactly the same as this mathematical way of thinking about it? Or like, yeah, how do physicists think about symmetry? I'll go to you,
I
Tim.
actually want to back up there because
Okay.
I feel like the description of symmetry you gave is actually quite sophisticated in terms of invariance.
Oh,
Because like most of the time when people think about symmetry, they think of like, oh, it's like the same left as it is to right.
oh,
Um,
okay.
but the formal version of that, that's true. Like if you see like a like a human body, for example, it's like left right symmetric approximately.
Mhm.
But what symmetry means technically, like when mathematicians speak about it, is it means you can change something about it and it's indistinguishable. So when you say that a human being is symmetric, you're saying that you could flip left and right and you probably wouldn't be able to tell the difference.
Mm.
Um, so for a circle, that has an even greater amount of symmetry because you can take a circle and you can rotate it any number of degrees and it's indistinguishable from what it was before. So a triangle, whatever, equilateral triangle has some symmetry, a circle has more symmetry. There's more number of ways I can permute it. I can modify it and have it be indistinguishable from its previous state. So really what we're talking about here is like equivalence, right? Like when we talk about symmetry of like gravity, like with the sun, we're saying that like as long as you're this radius, this distance away from the sun, you feel the same gravitational force. There's an equivalence. You could rotate the system and you wouldn't be able to tell anything because you'd be feeling the same thing.
Yeah, I think I would add that I don't think physicists generally, I don't think there's a specific viewpoint about symmetries that physicists take. There are many viewpoints. I think the, change without change is one of the viewpoint. You can also think of it as a systematic way of generating relationships. Take the example of a triangle, a equilateral triangle. Because we know that it has this kind of trifold symmetry, we know that all the angles are the same. We know that all the sides are the same, right? We know that the front and the back is the same. So there's a systematic way. If you tell me this object has this symmetry, I'll be able to generate these relationships for you. So in some ways, it's the systematization of understanding, of generating patterns.
Yeah, but change without change sounds cooler.
I like that too as well. Change without change. All right, so that symmetries change without change.
Yeah.
Okay, so I guess one question I want to ask is, so we originally, when starting out this episode, we talked about the 1/r squared law for gravity, and that it has this spherical symmetry that intuitively makes sense based on what I know, and sure the audience would also see it that way as well. But if I look at like galaxies or specific like our solar system, even it is not spherically symmetric. I mean, it's like close to cylindrically symmetric, or not even that. Almost, it has this ellipsoidal kind of like motion, but it's definitely not spherically symmetric. So my question to you is like, where did that spherical symmetry go?
You mean like the Earth because it's bulging as it spins?
No, okay. Imagine you take the Earth rotating around the sun. It's not orbiting around the sun in like a perfect circle. It's this like
Yeah.
ellipse.
Yeah.
And so my question, and that too for most planets. In fact, I haven't heard a case of a planet that's orbiting exactly circularly around like a star. So
Yeah.
where did all this symmetry go is my question.
Well,
I'd
so
say
yeah, perfectly symmetrical laws of physics can give rise to asymmetric orbits. Where does that come from?
I mean
Looking at
I think that's a common misconception, right? Like just because a theory has a beautiful symmetry does not mean that its solution will have it. Like for example, if I have let's say a deck of cards and I shuffle them perfectly, if I pick one, I have to choose a card, and that card will not if you let's say if you just get an ace, you would not know that I started with a perfectly shuffled deck of cards. In the same way, in our universe, we're dealt a solution, or the fact that the Earth is orbiting around the sun, it's a solution. That solution doesn't necessarily showcase all the symmetries because part of it is happenstance. And I think this highlights how important symmetries are because so many things about our world is just happenstance. We happen to live on Earth. The Earth happened to be in the solar system. These have nothing to do with fundamental physics. They just are the way they are, And the idea is, if we go to symmetries, we're kind of elevating ourselves to look beyond our particular situations, to see the bigger picture. So coming back to this question, yes, the gravity is spherically symmetric. Mm-hmm. And if you look at all the possible orbits, you see that they add up to a spherically symmetric way. If the sun is able to orbit in one plane, it can orbit in a different plane. If it can have this elliptical shape, the bulge could be bulged in another way. If you're able to look at all the solution together, so you draw all the orbits, you see that hey, they average out to spherically symmetric. But of course, we live on Earth. We're forced to pick one solution, and in that solution, the full symmetry of the system might not be apparent.
Gotcha. So if I'm understanding what you said correctly, it has to do with like you have the equations that govern physics have symmetries in them, but specific solutions such as like what emerges with the Earth orbiting around the sun, which doesn't have spherical symmetry, not even circular symmetry or like cylindrical symmetry, that is a particular instance of like initial conditions. But if you were to look across like a wide swath of like different galaxies or solar systems types, then you would find that it has like this spherical symmetry.
Yeah, and I would imagine if you take, let's say, all the solar system-like system in the universe,
Mhm.
you see that they will average out. You know, let's say take all the planets in our universe.
Mhm.
I don't know if we can get that. If you look at all their orbits, yeah, they'll probably add up to something spherically symmetric.
I mean, you could probably even
Gotcha.
argue that
Mhm.
if somehow the sun and the earth were to live forever, eventually you would find that the orbit is spherically symmetric over trillions and trillions of years.
Are, are you saying kind of like the precession of the ellipse itself?
Yeah, yeah.
Okay.
Yeah.
Yeah, that I buy that. Okay. So one I guess one this I assume the same argument applies to like, let's say things on Earth, for instance. Like you have like particles that exhibit symmetries, and we can touch upon that a little bit later in particle physics. And the stuff that is made up of these like particles that exhibit these symmetries themselves do not macroscopically have this symmetry. Like for instance, if I made like made a tree out of like let's say particles that had spherical symmetry, the tree itself wouldn't have spherical symmetry, but it made up of things that had spherical symmetry. So can I think of like complex structures in that way, or the loss of symmetries in complex structures? I don't know if that made any sense or.
Well, I think it made sense, right? The tree grew this way because there was an Earth and we happen to be on it, and the Earth has
Mm,
gravity, and that this biases the world around us, and then it creates complex things that are not as symmetric as they were before. And that's a good thing, you know. That's necessary, right? Like we know the stuff around us isn't perfectly symmetrical. Like it'll be a shame if my laptop has to be like a perfect sphere. Like I don't know how we can use it. So like this breaking of symmetry is a, I don't know, it's a, I guess it's a crucial fact, right? There are symmetries and they are broken.
got it, got it.
I think it's worth mentioning that, like, when you say like you take these symmetric things and make something that's in the end not symmetric, that's
Mhm,
not quite true. What we're taking are approximately symmetric things, and
mhm.
as we put them together, their asymmetry compiles into beautiful asymmetric structures, like life and stuff like that.
Yeah, that's really fair. Last question before I jump into before we move on to our next topic on this matter is, what is the most symmetrical object? This
That's tough.
Tim or Mikey.
Do you mean a physical object or an abstract object?
I guess whatever is easiest to explain. I guess maybe abstract, because physical I can think of like a sphere, or maybe just like an empty infinite space.
I mean, we're talking about like exceptional Lie groups right now, right? they're they're like mathematical objects that have been
Yeah,
um, discovered and sought after specifically because of their shockingly high degree of symmetry.
yeah, probably. I mean, this is very, very technical. What Lima's
The Yangian, right?
amplituhedron? There's a,
Yangian.
yeah, there's an infinite towers of, symmetry, Yangian symmetry. It's non-local. It's got supersymmetry. Like any symmetry you can think of that are important in physics, it pretty much has it.
Hmm.
But it's a very technical subject. But and Nima calls it the most beautiful, the simplest theory because it's got so many symmetries.
Yet it's such a complicated object.
Well, I mean, it depends on your perspective, right? Like
Mm,
what we were mentioning before.
It's such a
Equations are
complicated route to discovering it, but
yeah,
the thing itself is not complicated.
yeah. So the
mm,
problem is if you try to study this theory using equations, it's hopeless. There's so many bazillion of the equations. There are infinitely many equations because there are
mm,
infinitely many relationships to write down.
mm,
But if you take the perspective and say that, hey, look, these equations, they're just a viewpoint. They're like different snapshot of this object. And I can just say,
mm,
hey, I have an object described by the Yangian symmetry. then there's only one unique object, I think. And then you don't need any equations, right? So the goal of these studies is almost like to go beyond the constraints of equations and kind of elevate physics into just like, hey, there's this beautiful object described by this beautiful symmetry, and that's it. You don't even need equations.
Gotcha. Okay, yeah, that makes sense. Now I want to jump into particle physics. So if we think of the notion of like a particle, say an electron, for instance, it has some form of symmetry in it, I believe. I mean, if we look at the classical view of an electron, all I can say is like it has spherical symmetry. How does that change with like when you bring in quantum physics and quantum field theory or like, particle physics into the picture?
Well, I think the most salient example is the anti-electron, the positron. Once you
Okay.
bring in quantum physics, you uh, inescapably now have an antiparticle, and the particle-antiparticle symmetry is a very deep one.
I see. What is that? What is that symmetry like? What's the significance of that symmetry? Like,
Um,
I mean, there are two types. There are two types of symmetries, right? In physics, broadly speaking, one is, and this is a little technical. The one type is what we call a discrete symmetry. These are like mirrors. If you look at something in the mirror, it looks totally different. The other is what we call continuous symmetry, meaning that we can.
That's the same as like a square and a square and a circle. That's not. Yeah, people can understand that.
Yeah. Basically, you can continuously tweak it a little bit, right? So, Mikey, what you mentioning the particle antiparticle? I think in particle physics that's the charge conjugation invariance. That's one of the discrete symmetry, and there are some beautiful mathematical theories, theorems called CPT theorem, that guarantees that such a symmetry has to exist for sensible laws of physics. There are experiments that test it now, but yeah, I think it's a little hard to see its significance in real life, is it? Yeah.
No, I mean like the idea that particles and antiparticles, right? Like we're like it's right now. It's you can think about it as like a mirror symmetry. It's like binary, right? It's like 0, 1, 0, like particles 1 and particle 0. Like it's like a one or the other kind of thing. But once you increase the temperature, these particles, they really kind of just melt into a single symmetric object.
hold on, I want to unpack that. You introduced a new concept, so you gotta explain it. Well, you said increased temperature. Why are we? What does temperature have to do with anything?
Let's see.
I mean, would you? I can take a stab at answering it if you want.
Well,
I
okay,
think
no,
I know where you're
I
going.
guess if you want to get into it, I think it's probably worth talking about like the story about how symmetries can appear or disappear depending on the temperature. And so the classic example is that you think of like water, right? If you look at water, water molecules, they're polarized. So you can think of them as little arrows. And if you look at water, these molecules, these polarized arrows are pointing basically at random directions. So there's a spherical symmetry there. No matter which direction you look at, you'll see an equal number of arrows pointing towards and away from you. If the temperature starts to drop, then the water starts to freeze. And now all of these little arrows start lining up into like a lattice. And so the spherical symmetry you had is now broken because now there's a special direction. There's a direction where all of the arrows are pointing. And so that's a general, this like it's nice because that's like a very relatable example, but this happens a lot to symmetries in physics in all kinds of different contexts. When the temperature changes, symmetries can sometimes appear, sometimes disappear. We call breaking the symmetry.
Well, I mean, I think this is related to what we describe. Whether we see a symmetry in our world versus we only see one particular solution and we only see one aspect of it. And if you dial up the temperature, you're basically allowed to sample all the different possibilities. So
Yeah.
temperature
I
gives you
guess
that energy. Yeah.
real quick, I still want to draw the connection of like, what does temperature have to do with this? Because when I think of temperature, I think of like from a thermodynamic standpoint of particles bouncing around, hitting each other, and the higher the temperature, the higher the average kinetic energy per thing is. But here, like, I'm just trying to understand, like, how do I think about temperature? Like, what is temperature in this context? Like, am I in an oven? Am I like turning something on or off? Like, what do I think of that?
Temperature is something that allows you to explicitly see the effects of the symmetry when you increase the temperature. When you
Mhm.
decrease the temperature, like in the example of water, there could be symmetries in the system, but they freeze, for lack of a better word, and you have something that looks
Mhm.
less symmetric, less ordered.
So let me ask this instead. So in particle physics, I usually haven't seen the case. I mean, unless there are other domains I haven't explored, but I haven't seen the case where you have like a bajillion particles. It's usually like one or two particles interacting with each other in some way. They do something and you compute something. If I take the case of a single particle and take this analogy of like increasing temperature up to a certain amount and then decreasing it, like how do I think about temperature in this context? I'm just asking, like, if I have very few number of particles, does temperature make sense, or is temperature a proxy for something, or like,
Well,
Well,
if you increase the temperature, you're gonna you can't have just a few particles with a high temperature. You're gonna have lots of particles.
okay, so you're talking about like a full like a system of like many particles.
Yeah.
Okay, okay.
I mean,
Does this? Oh, go ahead, Tim.
because I'm not sure if we want to focus on temperature that much. I mean, it's just one neat point that earlier in the universe, the temperature is very hot, and some of the symmetries becomes more apparent. Basically, more particles are similar to one another because the temperature was so hot. There weren't energy barriers for them to not be able to convert to one another. So it's like a melting soup, and all the particles talk to each other, then convert to each other, and so the temperature, the symmetries become more apparent. And as the universe cools down, we see particles pick up different identities, basically. Like the electrons
Mhm.
become different from the neutrinos. And if the temperature was hot enough in a thermal bath, the behaviors would be very similar. And I think that's, Mike, what you're referring to. But I mean, technically,
So,
you can access it in different ways, theoretically. But temperature is one physical way you can do that.
mhm. So one question about that's actually really interesting. You bring that up. Is this notion of at sufficiently high temperatures, like in the early universe, particles transforming to other particles. Does that mean like an electron can transform into a proton, or how does the conservation of charge work and all these other like different conservation laws work, like
But no,
conservation of
conservation of
energy
charge
and stuff
still
like
holds.
that?
Yeah, conservation of charge still holds, but
Okay.
yeah, basically, there's so much energy in the empty space that a particle can just borrow energy to
Mhm.
increase its mass and turn into another particle, as long as you know none of those
So,
conserved quantities are broken.
Yeah, but
so,
you
so,
can't just convert an electron to a proton because they're not related by any symmetries. Only if there
mm,
are symmetries relating them, you can do
Yeah,
that. For example, I mentioned this example: an electron could convert into a neutrino, an electron in a
mhm.
neutrino. You can't do that right now. It will require a lot of energy. You have to inject a lot of energy in your system to do it in a particle accelerator. But if the temperature is very, very hot, it's able to borrow that energy, then yeah, that conversion will be effortless. And it also happens in centers of stars when it's really hot. So that hints at asymmetry, and this is called the and this is the basis of the weak force. The weak force is based
Mhm.
off of asymmetry, and the relationship between the neutrino and the electron is the weak charge, right? Is it weak isospin? And people are not familiar with it, but they are related by asymmetry.
Okay, so you have the symmetry between like particles that I don't I want to use this term very loosely, like embody this one of the fundamental forces called weak force
Mhm.
that's responsible for like nuclear decay and all that stuff, like neutrons decaying into protons, electrons, and neutrinos, those sorts of processes. And then your standard like electromagnetism of like electrons and maybe other particles of similar type of family of those type. And there's a symmetry between going from one to the other. Is that did I get that right?
Yeah, I think symmetries allow you to kind of understand why one particle is able to convert to another in a much simpler way.
Hmm.
Like because one perspective, you can take the perspective of chemistry. Hey, there's this massive table of conversion rules that could happen between particles, and you can just say, well, it's just the way it is, right? That's one perspective. Or alternatively, you can say, hey, look, we have these symmetries, and because of these symmetries, groups of particles are able to convert into one another, and that can organize your information much better. And that's the perspective that particle physics takes.
Mm, gotcha. So one thing I want to move towards is like, okay, so this is actually really interesting. So you mentioned that if you at a high enough temperature, things, I mean, assuming they're within the same symmetry groups, things can like become each other, and it's hard to distinguish really between the two. They can transform into each other because you just have so much energy to borrow from. You can become a particle of a higher mass, provided all the conservation laws hold. And then as you decrease the temperature, you no longer see that. Like we don't see electrons transforming into other particles. I mean, as far
Hmm.
as I can tell, like we're not transforming into like other, other things. And so my question for you is like, where did all that symmetry go? Is it can you use the same analogy with like the galaxy thing that we were talking about? How it has this like solar system, like it doesn't have the spherical symmetry anymore. Like is there the same analogy or is it something completely different?
I think the water analogy is the best analogy, and it's the same as
Mhm.
Tim analogies. Like like it's by happenstance. Like when water freezes, it could have been all the arrows are pointing north, or it could have been by happenstance all the arrows ended up pointing up south. But when you decrease the temperature, you decrease the ability of things to vary, and things settle into a frozen state, and frozen states typically have less symmetry than active states. I don't
Yeah,
know. Anything I missed, Tim?
no, I think that's a fair analogy, and I think it goes beyond just like the universe was hotter. I think you can think of you can think of the entire trajectory of the universe. We went through Big Bang, galaxies, and whatnot, and particles come to the way they are. It's kind of like a snowflake being formed, right? Like imagine you just have a cloud of water vapor. As it cools down, it formed this very delicate structure, a snowflake, and they're very intricate patterns. And if we as we study this snowflake, we notice things are very intricate. Maybe the six corners of it had this beautiful pattern, right? And just like what we're discovering, there's some very intricate patterns between particles. But I think in the grand scheme of things, for physicists, we deeply believe that at least I do, the equations that discover a large part of it could just be due to happenstance. Even the fundamental equations of particles, yeah, like the fact that neutrinos and electrons are related, and maybe just maybe there are concepts beyond this equation, right? Like maybe if we look at the entire multiverse of possibilities, each little universe will have slightly different equations, right? But then the common denominator, will be beyond those equations, and those will be the symmetries. So symmetry will be what we mean if we look beyond our equations and think of them as just happenstance. And I think that's a very common viewpoint. Yeah,
Terrible.
terrible viewpoint.
Wait,
I
what do you think is terrible about that?
don't know. It's just we'll never know the answer.
I guess okay, so one natural question that I have is is it fair to say that like in the earliest universe, whatever that means, that the object that existed had like the maximal amount of symmetry?
Highly likely.
I think we would hope to believe it. Yeah.
I mean,
I mean,
every time we increased the temperature or looked at a shorter distance, the symmetry's increased. Um, yeah, there's a lot of beautiful possibilities. It would be weird if it just sprayed out into chaos again. But not impossible.
I mean,
gotcha.
it's plausible that at the beginning we have something like the amplituhedron. It's the maximum amount of symmetry. I think some people would believe that.
Tim, one question to engage in my own indulgence. Is it more symmetrical than the monster group?
Oh, it's way more, I think.
Oh,
Wait,
okay.
no,
All
what?
right.
Oh, yeah. Well, the monster group is like it's different. Like you can count the discrete symmetry. It's different when you have like a continuous class of symmetries, right?
Yeah,
Oh, I see.
it's completely different class. The monster group is the largest what is it? Semi-simple, I don't know, discrete group. I think I'm
Yeah,
mixing up jargon.
it's
We're
like
talk
comparing prisms with circles.
Yeah, we're talking about like
Okay.
yeah, we're talking about I don't even know how you compare it. It's just yeah, the Yangian
Because
symmetry group. Yeah,
it also has continuous symmetries, is what you're saying.
yeah. It's way larger. Yeah, it's got all
Okay.
kinds of continuous symmetry. It's not even in the same class. So
Got it, got it. It's like comparing like a rectangle to like a circle in terms of symmetries.
no,
Like if I were to draw it.
I think it's more crazy than that. It's comparing like a like a square to like an infinite dimensional fractals of circles popping in and out, zooming in and out.
No, it's like to be fair, it's like comparing an infinite dimensional fractal of squares to an infinite fractal of circles.
All right. Well, I don't bore the audience too much. Um, okay. So I guess where does this leave us? Like I guess like how does particle physics proceed with all the symmetry stuff? Is it just a question of probing higher and higher energies and being like, oh, I guess we can merge, symmetries together?
I don't know, nothing's working.
Well, I wouldn't take such a
Very
I wouldn't take such a pessimistic view. So we know that our world it's kind of like the remnant of a more symmetric world, and of course the simplest way to probe what the earlier world was like is to access these high energy. That's why we build massive colliders to smash things together. But there are other ways. There are more subtle ways to look for these symmetries, right? Like you can look at hints, leftovers of these symmetries. And I know we haven't discussed these. Symmetries, if they were obvious or they were hidden, have consequences. They're not just like pie in the sky abstract ideas. And physicists have tried very hard to run various different experiments to look for these remnants.
hmm. Any thoughts on that, Mikey? Are you still
Yeah, it's
maintaining a
hard. It's
more
hard.
All right. So, two things. One is we're almost at time, so I want to, in tradition, I want to give you guys a chance to leave the audience any few words of wisdom. And then the second thing is I want to after we do that, kind of like a post episode uh reading of the a particular audience member's comments relating to fractals. Actually, we talked about fractals very briefly, but yeah. So anything you want to give the audience as words of wisdom that
Uh,
symmetries have taught you?
yeah, I'll be the curmudgeon. Um, yeah, I don't know. It's kind of sucks. It seems like we're at a fork in the road where for 400 years, um, every single theoretical advancement has come from like the discovery of like greater and greater symmetries being applied to physics. And it didn't work the last time around. So, maybe this is just a particularly tricky era, or maybe the idea of using symmetry to organize the laws of physics, at least at these temperature scales that we can access. Maybe that's just not the tool for the job right now. But I mean, I don't want to understate the importance of symmetry and understanding of the universe and just in terms of like how it displays like the elegant structure of it. But yeah, whatever the next big thing is in particle physics is going to require something bigger than traditional notions of symmetry.
I mean, I guess personally, I wouldn't be as pessimistic. Maybe partly because I've left the grind of academic research, but I do still firmly believe that, you know, this notion of symmetry, while it might require some modification, is our best way of gaining this bird's eye view of physics. You know, really, equations and all these complicated math, that's not it. There is a beautiful way to look at physics. And physics is about patterns, about discovering, it's about explaining why equations are the way they are. And I think symmetry is our best way forward. And like Mikey said, maybe this notion has to be modified a little bit. And in the following episode, I think we'll explore some of these different symmetries. One of the more well-known ones is supersymmetry. And that, back in the days, required us to tweak our notions of symmetry a little bit. Perhaps in the future, we need to tweak it a little bit more as well. So I wouldn't give up on this idea just yet.
I guess, Tim, one thing I wanted to ask you about regarding that is that, like, could you explain to the audience how much, like, I guess, how much better it is to use symmetries to guide your way of thinking rather than just writing down equations? Like, what is the difference of starting with equations versus starting with symmetries and then going to equations?
Yeah, I think in the simplest scenario, you get to the same place. I mean, for example, you can take the example of Einstein, right? He discovered relativity. Initially, the equation is very complex, pages and pages, 3 to 4 pages. You can write them down and eventually simplify them into 1-2 lines, right? If you started with this notion of symmetry, that, you know, the shape of the space-time doesn't matter, the physics is inherent. It does not depend on the shape of the space-time. You can just write down the equation, 1 line. But of course, that's after like 100 years of insight to know that, hey, look, you know, you can explain Einstein's equation using symmetries. So if you have that hindsight, symmetry is vastly more powerful. Yeah. And the way we learn physics too, you know, initially it's all about these equations. It's difficult to solve them. But symmetries offers us a lot of shortcuts quite often. You can just be like, it's a 1-line solution. So I would say the difference is dramatic. Sometimes you couldn't even solve anything without using symmetries. The only way forward is using symmetries, I would say.
Yeah, let's be clear, we wouldn't be able to solve anything, period, without symmetries.
Do you agree with that, Tim?
Well, in very hard problems, you probably have to use symmetries, but in very, very simple problems, you can probably...
If there were no symmetries in nature, then nothing would be solvable.
Well, yeah, sure, but I'm saying you can...
It would be chaotic.
I'm saying if you ignore them. If you have symmetries, like, well, let's ignore them. Let's just grind through it like a good old calculator. I don't know, yeah. If you're just like a good technician calculator, you just grind through the equations.
No,
yeah,
a computer can simulate anything, yeah.
Like you can just brute force it, but it's not elegant, right?
Mm-hmm. All right. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, what about these audience questions?
Oh yes, I want to just like let the audience know that they don't have to stay in this portion if they don't want to, because these are some technical comments. But yeah. All right, let's do it. Okay, so an audience member mentioned, I hypothesized there might be a hidden symmetry in the quantum world, self-similarity. One can increase or decrease a magnification of the Mandelbrot fractal. Accordingly, it may be possible to go to low energies and back in super deterministic theories, UV to IR, back to UV.
Then just talking about conformal field theory.
And then a wonder could hide in the super deterministic analog of the renormalization group equations. I understood like half of that, or maybe like I understood each word individually.
I don't think super deterministic is a word.
Yeah, I don't think that's a technical term. Not clear what the
Yeah,
audience
but
is
he's just
referring to.
talking about conformal field theory. Just tell him to go read about conformal field theory.
Yeah, I mean, I can comment on that. Physicists have wondered whether this zooming in, this fractal-like behavior, it is a legitimate symmetry, right? You zoom in, you see similar structure. This
Yeah,
self-similarity,
very
and
important.
it's generally referred to as conformal symmetry, but unfortunately, in most theories, it does not exist unless you really fine-tune the parameters. You can do a calculation and you see that hey, it's not a given that you have it. And of course, in string theory, it's inherent that you have to have conformal invariance. So if you believe in string theory, yeah, some of that will have to exist.
Yeah.
So the answer is we don't know. We and like I said before, if there's a symmetry, if it's obvious, they are mathematical consequences. And if they're hidden, they're also mathematical consequences. And these comes in through conserved quantities, or what we call light particles from the hidden symmetry. These are Goldstone bosons, and these will need to be experimentally verified. For conformal symmetries, we know that it has to be broken because we don't observe them in the world, and
Yeah.
the corresponding particle will be a dilaton. We have not seen dilaton yet, so it's speculative.
Did you say dilettante?
Yeah, it's a particle arising from the destruction of the self-similarity symmetry.
Because if I remember correctly, like dilettante in like common vernacular is like somebody's like dumb or something like that. Like, oh, this
No.
person's a dilettante.
I'm not sure, but
No.
that's a technical term. Yeah, it's a particle associated with the consequences of this hidden symmetry. So yeah, if we find a hint of dilettante, which has to do with gravity, because has to do with the zooming in and out of space-time itself,
Mhm.
yeah, then we'll prove that there's a self-similarity symmetry, but we haven't seen anything like that yet.
But beyond that, if you're interested in fractal structures inside microscopic distances, there's people have thought about this to death. There have been a lot of really, really fascinating results. A lot of theories do exhibit fractal behaviors for a large part of their distance scaling. And this has many, many important consequences. You could argue that some of these fractal structures that exist at microscopic distances kind of, what's the word? Like reincarnate themselves at larger distances and give rise to some of the fractal patterns that we see in nature. So, there's a ton that's people have thought about it a ton, and a ton has been written on it. So if you want some literature recommendations, let us know.
Yeah, do join our Discord channel as I keep preaching in the beginning of every episode. Yeah. So on that note, is that all you guys wanted to say about this
Yeah.
comment?
Yeah, I think so.
Okay. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Bye-bye.
Bye-bye.
Bye.